Hello, everyone. Welcome to our week two for this course, Physics for Engineers. Okay, so this morning we are going to discuss Module 2, which is all about motion. So, first and foremost, we have the motion along the horizontal, motion along the vertical, and lastly, we have our motion for two-dimensional, which will be the projectile motion, both having the x and y axis. Okay, so let us first review on the equations that we had in our senior high school or in junior high school with regards to motion. Okay, so talking about motion, I will be sharing to you my notes. Wait for a while. Talking about motion, of course, we already learned about the speed, velocity, acceleration. Okay, so when we talk about the speed, that refers to distance per unit time. Okay, the rate of change in position. So when we say speed, that is only a scalar quantity. Well, the vector quantity for that is velocity. So for velocity, we have both the direction as well as the magnitude. But for speed, it is only magnitude. Okay, so sharing to you my notes so we can refresh our mind with our equations for linear motion. Okay, so let us start first with linear motion or motion along the horizontal. Okay, so here it is. Wait for a while. I will delete all and I will create another page first. Okay, sorry guys. Bear with me for a second. Okay, there you go. Okay, first is we have our I should have rotate this. Na-rotate na, wala na-rotate. Okay, there. Alright, so let us first have a review of our kinematics equations. You have this in your junior high school and senior high school already, okay? So when we say kinematics, this refers to motion. Okay, so an object moves along the x-axis. Of course, we can quantify the motion of the object. We can solve for the speed or the velocity of the object. Okay, now this time we will be focusing on the speed. Okay, so an object coming from a position x sub o, that is the initial position of the object, and x is the final position of the object, and x minus x sub o, we can call it as distance. Okay, so that would be equal to the average speed, of course, along the x-axis multiplied by the time. Okay, so when we say average speed, that is the initial speed or velocity plus the final velocity divided by 2. All right. So another kinematics equation, we have our final velocity that would be equal to the initial velocity plus at, where a is acceleration. Okay, now acceleration is the time rate of change in speed or velocity. So when we say acceleration, that will just be equal to the velocity divided by time. Okay, so for velocity, we have our unit meter per second, while for acceleration, the unit is meter per second squared. All right, and another kinematics equation, distance will be equal to the initial velocity times time plus 1 half at squared. Okay, where v sub o is again the initial velocity. And lastly, we have v squared minus v sub o squared. That will be equal to 2a multiplied by the change in the position or the distance. Okay, so these are our four kinematics equations that we can use in order to solve problems with regards to motion along the x-axis or horizontal motion, as we say. Okay, now we also include free fall. Okay, when we say free fall, this is the the universal gravitational law of Newton. Okay, so we already learned about that in your junior high or senior high, or if you had already minor understanding for physics. Okay, so Newton said that all object is pulled towards the Earth's core by gravity. Okay, so we have our 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 constant value for the acceleration due to gravity g, which is 9.8 meter per second squared. Okay, that is the pull towards the Earth's core. Okay, in a vacuum. Okay, so everything according to the law, everything falls down at the same time when it is in a vacuum. Okay? No matter what the mass of the object is, but it falls down at the same time in a vacuum. Okay, that has been experimented by our dear scientists and ancestors. All right. So for free fall, this is no motion along the vertical line or along the y-axis. So instead of x, we are going to use y, and instead of x sub o, we are going to use y sub o. And instead of the acceleration, we are going to use the acceleration due to gravity. And this time it is negative g because of the direction it is going down. Okay, so below our datum for the negative y-axis. Okay, so going down. So our kinematics equation will then become for free fall to be y minus y sub o is equal to v sub y, this time the average times the time. Okay? And we have for our second, V is equal to VO minus GT, or V sub O. Rather, Y minus Y sub O, V sub O times time minus 1 half GT squared. Again, take note we are using negative because of the acceleration due to gravity, which is going towards the Earth's core or going downwards. Okay, so we have also, and I still use this part here. All right, very good. V squared minus V sub O squared, that would be equal to negative 2g times y minus y sub o. Okay, where did I take these equations? I take these equations from our kinematics equations above. So again, for free fall, we just change the x. Instead of x, we change it into y. And instead of a, we change it into negative g. So we have now our four kinematics equations and our four equations for free fall. Now let us proceed to the motion, which is two-dimensional, both along the x and along the y. Okay, just like that. All right, so let us now proceed to projectile motion. Oh, what is happening? Okay, so projectile motion. Okay, now for projectile motion, sorry, as what I've mentioned earlier, we now have two-dimensional motion, both along the x and the y. Okay, so for projectile, it follows a curved path. Okay, so we have what we call as a projectile, which is our object, and the trajectory, which is the curved path that our object is taking or following. Okay, so for this, if we have a projectile, we are throwing our object at a certain angle. Okay, so we exert an initial velocity at a certain angle. Okay, so here we exert an initial velocity VO, that is our initial velocity, at a certain angle. All right. Now, since we have our initial velocity at a certain angle and we say that velocity is a vector quantity, okay? Therefore, we can get the components of this vector quantity. So the component for our initial velocity, we have, I will change the color. We have our initial velocity along x, and we also have our initial velocity along y. Okay, we are just separating our initial velocity into its x and y components. Okay, now since our projectile is going up, going towards at the highest point here. Okay, so our projectile again is the object. It follows a curved path, and what we call the curved path is a trajectory. All right, so there is, of course, the velocity here at the highest point. Okay, and our velocity also here at our endpoint where our projectile reaches. So this will be our final velocity. All right. We can also have this velocity at the highest point to be our final velocity. Okay. So since it is again a vector quantity, we have our x component and our y component for our velocity. So that is our x component and that is also our y component. Okay? So with that, for our projectile, we also have the range. Okay, the range will be the distance, the distance from where our projectile has been launched to its final destination. So that is the range. And of course, if we have the range, we also have the maximum height. Okay, that is the maximum height where our projectile reaches. Okay, so say for example, you are playing golf. Okay, where does the ball of the golf come from? Okay, it comes from the ground, right? And when you hit the golf ball, okay, you hit it from the ground, so it will go up at a certain angle. Okay, so once it goes up, of course, it will come back down to Earth. Okay, because of the pull of gravity. So that is our projectile motion is all about. All right, so let us have our equations for projectile motion. So just like the kinematics equations, okay, we are only taking our equations from the kinematics equations and of course the free fall. So for the horizontal, our equations would be P sub OX is equal to Vx. Okay, why would that be? The initial velocity of our projectile is equal to the final velocity along the x-axis of our projectile. All right, so there will be no change in the magnitude of the velocity along the x-axis. They stay the same no matter where the projectile is in the trajectory. Okay? So our range we have it as x minus x sub o, the distance wherein the projectile was launched and the endpoint of the projectile. So that is equal to v sub ox times t. And we also have our equations for the vertical. Okay, so we have v sub y is equal to v sub oy minus gt. Again, we are taking this from the free fall equations. Y minus y sub o is equal to v sub o y times time minus 1 half gt squared. There must be squared there. Okay, and v squared minus v sub o squared is equal to negative 2g y minus y sub o. Don't worry guys, all of these equations are in your module. Okay, if you cannot read properly my penmanship, all of these equations are in your module. All right, so with that, we also have take note, since we have our x component of the velocity, never forget, okay, so the SOHCAHTOA, v sub ox is equal to the initial velocity times cosine theta. Okay, never forget that. SOHCAHTOA. Okay, so if we are going to go back to our illustration, our v sub o, our initial velocity is here. This one, initial velocity. Okay, so and v sub o is here. It is adjacent to our angle. Okay, so once it is adjacent to our angle, cosine. Okay, ka, cosine is equal to adjacent over hypotenuse. All right, so let us now have our example. I will share to you my screen, my other screen, and kindly take a photo. Okay, is it there already? Kindly take a photo of the problem. So by the time you are going to solve the problem, you can glance at the problem. Okay, I will check if my screen is there. What is happening? Okay, my screen is there already. Okay, now we are asked, in what angle would you likely shoot the ball if you are 4 meters away from the ring and you exert force with a speed of 20 meter per second in 0.31 seconds? Okay, so we have our illustration there. Okay, just imagine you are an NBA player. Okay, so by the way, the picture is taken from the web. Okay, now, you are asked what angle are you going to use in order to shoot it. You are 4 meters away from the ring. So maybe you are drawing lots with this. I'm not familiar with basketball anyway. So now you exert a force and the ball goes at an initial speed of 20 meter per second. And the ball reaches the ring in 0.31 seconds. Okay, so how are we going to solve that? Again, kindly take photo or screenshot of the problem so that later when we are going to solve it, you can glance the problem. Okay, you can glance at the problem rather. Okay, so let us share my notes again. And let me check if it's there. And I guess my notes is not yet there. Did I share? Okay, there you go. All right, so let us answer our problem. Okay, first we have to identify the given. Okay, we are given the range, which is 4 meters. We are also given the initial velocity, which is 20 meter per second. And of course, we were also given the time, which is 0.31 second. Now, what is asked in our problem is the angle. Okay, now going back to our equations for projectile motion, we can easily identify which equations are we going to use from the given. Okay, so we were given 4 meters, that is the range. So where can we have that? We have here the range. Okay, so maybe we can use that formula. Now, we are given the initial speed, which is 20 meter per second. So, if we are given the initial speed of 20 meter per second, okay, so it is here. Maybe we can use this formula. Okay, now we are given the time. The time is 0.31 second, and we have the time here. So maybe we can use that formula. Okay, so what will happen now? We are given the range, we are given the time. We can solve for the initial velocity along the x-axis. And since we have solved for that, we have the value for it here. And that's the time that we can solve for the angle, which is theta. Okay, that one. Okay, so first we have to solve the initial velocity along the x-axis. Okay, so initial velocity along the x-axis, we can use the formula x minus x sub o is equal to v sub o x times t. And x minus x sub o again is our range. So we have 4 meters is equal to v sub x times the time, 0.31 seconds. Okay, so use your calculator, guys, in solving for the V sub OX, and it is equal to 12.9 meter per second. Okay, now we can use this for our next equation, which is V sub OX is equal to V sub O times cosine theta. Okay, so we had solved for V sub OX. It is 12.9 meter per second. And that is equal to, what is our V sub O? The given is 20 meter per second. So we have 20 meter per second times cosine theta. Oops. Okay, so dividing both sides by 20, okay, and getting the inverse cosine for that, inverse cosine of 12.9 over 20. I do away with the units already because it cancels out. So our angle is 49.83 degrees. Okay, so what are the choices in our problem? The choices were 30, 50, and 70. So that would be around 50 degrees. Okay, so that's just how you're going to solve for problems in projectile motion. Okay, so if you have any questions with regards to our topic, don't hesitate to inbox me on Canvas. I am just an inbox away. Okay, so your module will be, the deadline for the submission of your module is due on February 27 midnight. Okay, so kindly take note of the deadlines and kindly take note of what I had posted in your announcement. Stay tuned every time and do your best. Okay, so please start working on your module before Wednesdays of each week. See you for our consultation hour, Wednesdays 6:40 to 8:55 a.m. Thank you very much, guys, and don't forget to subscribe to this channel and to my other channel. See you again next week.